All right, now we're going into our next and final chapter, container security. So here's a basic introduction to it. Container security has become a critical concern for enterprises as containers have emerged as the primary technology for deploying applications in modern IT environments. Without robust security measures, containers can introduce significant risks, including data breaches, downtime, and compliance violations. So what is a container? A container is a lightweight, standalone, executable package containing everything needed to run an application. That's code, runtime, libraries, system tools, and dependencies. Unlike traditional virtual machines, containers share the host operating system's kernel, making them far more efficient and portable across different computing environments. So here's some key terminology for containers. A container is a lightweight standalone package that encapsulates an application and its dependencies. A container host is the physical or virtual machine that runs containers using a container runtime. A container image is a static package of a container's content stored in a container registry. A container runtime is the software that runs the containers, like Docker or Containerd. The registry server is the repository that stores container images. Think Artifact Registry. Kubernetes is an open source container orchestration platform for automating deployment and management. And a pod is the smallest deployable unit in Kubernetes, consisting of one or more containers. So here's some security advantages of containers. These benefits include ephemeral nature, meaning containers are short-lived and frequently redeployed. They're immutable, meaning they're properly designed. If properly designed, containers shouldn't change after deployment, and modifications can trigger security alerts. There's default security. So good security defaults can be implemented with minimal configuration. And they're isolated, meaning these built-in isolated technologies improve security without adding resource overhead. And there's consistency. So the same container image runs in development, testing, and production environments. So here's some container basics. So traditionally, applications are deployed on dedicated servers through a lengthy process. You'd purchase the hardware, install the operation systems, configure the dependencies, deploy the application code, and ensure consistency across environments. This was time-consuming, resource-intensive, not portable, and difficult to scale. Now, how do containers work? So containers share the host machine's OS, the operating system kernel, and use containerization technology to isolate applications from other processes. Since they don't need to include a complete operating system, containers are much smaller and faster to start than virtual machines. So here's a couple of definitions to remember. There's a traditional model, right? These are applications deployed directly on bare metal or virtual machines. They're not portable and they're slow to scale. Then there's virtual machine based. Each application runs on its own operating system using hypervisors. And then there's container based. These are applications that share the operating system kernel but run in isolated processes. They're faster and more efficient. So here's a container structure. There's a layered file system where one, there's a base image layer and they're read-only. Two, there's a small read-write layer that sits on top for application-specific changes. And three, each container has its own writable container layer where all changes are stored. This structure enables efficient storage and rapid deployment of container instances. So here's some advantages of containers. Environment consistency. Applications run the same way across development, testing, and production. Efficient packaging. Containers only include what's needed to run the application. Microservices support. Containers are ideal for microservices architectures. Faster time to market. Small features can be developed, tested, and deployed multiple times daily. And simple rollbacks. Previous container versions can easily be restored if issues arise. So here's a Kubernetes overview. Kubernetes, or K8s, is an open source system for automating deployment, scaling, and management of containerized operations. So it serves as an orchestrator for container fleets, handling the complexities of container placement, networking, scaling, and healing. So here's some key Kubernetes components. The pod. This is the smallest deployable unit in Kubernetes, containing one or more containers. There's the service. This is the stable endpoint and load balancer for accessing pods. Then there's the namespace. This is the virtual cluster inside a Kubernetes cluster for resource isolation. Then there's the kubelet. This is the node agent that ensures containers are running in a pod. Then there's the kube proxy. This is a network proxy maintaining cluster network rules. Then there's a control plane. This is the central management component that includes scheduler, API server, and controller manager. And finally, there's the etcd. This is the distributed key value store for cluster state. Now here's some Kubernetes features. Load balancing and service direct discovery. Load balancing and service discovery. This exposes the containers via IP address or DNS names. Then there's storage orchestration. This mounts storage systems to containers. Then there's automated deployments and rollbacks. This updates applications based on declarative configurations. Bin packing, BIN, right? This automatically places containers based on resource requirements. Self-healing. This replaces failed containers and kills containers that don't respond to health checks. And secret and configuration management. This securely stores sensitive information needed by applications. So Google Kubernetes Engine. This is the managed Kubernetes service that simplifies the deployment management and scaling of containerized applications using Google's infrastructure. So GKE provides the following components. One, the GKE control plane. This is managed by Google, includes the Kubernetes API server, scheduler, and control manager. Then there's customer node VMs. These are worker machines that run application containers. Then there's the cluster. This set of worker machines, nodes, that run containerized application. Then there's the pods. These are the smallest deployable units encapsulating one or more containers. Then there's the services. These provide stable networking endpoints for pods. And the load balancers distribute traffic across nodes and services. Then there's the persistent storage. Persistent storage. This is the option for durable data storage. And finally, there's a container registry. This provides private registry for storing container images. So there's also the GKE shared responsibility model. In GKE, security responsibilities are divided between Google and its customers. Google is responsible for hardware, firmware, kernel, operating system, storage, and network infrastructure. Also responsible for the node operating system. This is the containerized operating system, or Ubuntu, with automatic updates. Then they're also responsible for the Kubernetes control plane management, and finally, the cloud service integrations like IAM, logging, and KMS. Customers are responsible for application workloads and their security, keeping nodes updated, which can also use the auto upgrade feature, the IAM roles and permissions, the network policies and firewall rules, and the container image security. So there's some container security risks. And NIST defines these container security risks in the following categories. One, image risks. These are configuration defects, embedded malware, secrets in images, and untrusted images. Two, registry risks. These are insecure connections, stale images, and inadequate authentication. Three, orchestrator risks. These are unrestricted admin access, unauthorized access, and poor network separation. Four, container risks. These are runtime vulnerabilities, unbounded network access, and insecure configurations. And five, host operating system risks. These are large attack surfaces, shared kernels, and vulnerabilities in host components. So the core security layers in Kubernetes and containers, Google encompasses three primary layers. One, infrastructure security. This will be API protection, privilege controls, and network security. Two, supply chain security. This means signed images, vulnerability scanning, and secure build processes. And three, runtime security. This includes least privilege, monitoring, DDoS protection, and threat detection. Google GKE has security features built in. So GKE provides newer security features to protect containerized applications. This includes namespaces. So namespaces are logical separation in Kubernetes clusters. They let you separate resources within a cluster, apply resource quotas to different teams or projects, and isolate workloads based on security requirements. There's also access control, and GKE supports two complementary access control mechanisms. One, Kubernetes role-based access control, which is RBAC. And RBAC controls are permissions at the cluster level through three ways. One, roles. These are namespace level permissions. Two, cluster roles. These are cluster-wide permissions. And three, role bindings. These connect users or groups to roles. For example, to create a role that allows users to review pods, you should use the following for your YAML. With the ABI, RBAC, the role, namespace default, name, pod reader, the API groups, the resource with the pods, and what can it do? Get, watch, or list. Okay. Two, identity and access management. IAM manages permissions for Google Cloud resources at the project level. This determines who can do the following: create or delete clusters, upgrade clusters, or access cluster metadata. IAM works alongside RBAC, with IAM controlling project level access and RBAC handling cluster level permissions. Now there's secrets management. Kubernetes secrets store sensitive data like API keys, passwords, TLS certificates, and OAuth tokens. Instead of embedding these values in container images or pod specifications, secrets provides encrypted storage at rest, access control through RBAC, and integration with external secret management systems. Then you have auditing. GKE integrates with cloud audit logs to record security relevant events. This includes admin activity logs, which is enabled by default. This will record, create, update, and delete operations. Then you have data access log, which must be enabled. This will record read operations and access to secrets. These logs help answer critical security questions like what actions were performed, when did they occur, who initiated them, and where did they originate. Then you have logging and monitoring. GKE provides comprehensive logging and monitoring through cloud logging, which collects container logs and system events, and cloud monitoring, which tracks cluster health and performance metrics. Let's go over here and take a look at the Kubernetes engine so you can get a visualization of this. Oh, whoa, that was not supposed to happen. So check that. Okay, so let's click this from the main window. Okay, so these tools help detect anomalies and potential security incidents in real time. So then there's network security. So there's network policies. These policies act as a firewall for pods, and they control which pods can communicate with each other, which external services pods can access, and what protocols and ports are allowed. So let me show you an example of a network policy that allows traffic only from specific pods. I'll copy, paste that here. So this shows the networking.k8s.io v1. Network policy is the kind. The metadata shows allow front end only. Then just spec will show the pod selector, match the labels for the database, and show the ingress from the pod selector, match the labels to front end, and the port 3306. Okay, so then you have private clusters. GKE private clusters enhance security by assigning only internal IP addresses to nodes. It prevents node exposure to the internet, and it restricts API service access. All right. Then you have service mesh. All right. A service mesh provides enhanced security for microservices communications through mutual TLS, which is MTLS encryption, fine-grained access policies, traffic monitoring and control, and certificate management. So then there's some container and image security best practices. Here's a best practice. Use a trusted base image. Start with Google maintained images from gcr.io/gc/distrolist. All right, that's it. Exclude secrets from images. Use Kubernetes secrets or external secret management. All right, so here's the secrets, config maps. All right. Apply updates and patches. Keep dependencies current to prevent vulnerabilities. Scan images for vulnerabilities. Use tools like artifact analysis or Trinity. Let's see. All right. Implement binary authorization. Okay. This allows only verified images to deploy. Minimize image size. Include only necessary components. Run as a non-root user. This avoids running containers with root privileges. And then use multi-stage builds. So with separate builds and runtime environments, you can build the image more successfully. So here's some container registry security that you should always implement. 1, implement strong security authentication and authorization. 2, use encrypted connections for all registry communications. 3, apply least privilege principles for registry access. 4, regularly scan and update images. 5, implement image lifecycle policies. So container vulnerability scanning. Google provides built-in vulnerability scanning for container images through the artifact registry. Let's see if we can get this. All right. Okay. And I'll add this to the chat. You can have this resource to look. All right. So this two scan types. One, on demand. This is manual scanning via the G-Cloud CLI. And then two, you have automated. This is continuous scanning of images in artifact registry. Vulnerability scanning detects known vulnerabilities in operating system packages, critical security flaws in application dependencies, and misconfigurations in container images. When automated scanning is enabled, vulnerability occurrences are created upon image upload. Metadata is updated as new vulnerability information becomes available, and images are pushed or pulled in the last 30 days, and they're continuously monitored. Vulnerabilities are rated by severity. At top would be critical, then would be high, then medium, then low, then minimal. Okay. Then we have binary authorization. Okay. All right. All right. I'll add this. All right. So binary authorization is a deployed time security control that ensures only trusted container images are deployed to GKE. So here's some key components. Policy. These are the rules defining which images can be deployed. Attestation. This is signed proof that an image passed security checks. Entity, or signer. This is the entity that creates attestations. Verifier. This is the emission controller in GKE that validates attestations. So how does binary authorization works? It defines a policy specifying required attestations for deployment. The images undergo security scanning and testing. If successful, authorized signers create attestations. During deployment, GKE verifies attestations against policy, and images without required attestations are rejected. So here's some use cases. If you want to enforce vulnerability scanning in the CI/CD pipeline, if you want to require security review before production deployment, if you want to ensure images come from a trusted build system, or if you want to prevent deployment of images with critical vulnerabilities. Certificate or authority in GKE. GKE uses TLS certificates to secure communications between cluster components. One communication type is API server to kubelet. This uses a cluster root certificate authority. Another one is etcd through etcd. This requires a separate etcd certificate authority. Then an optional one would be pod to pod. This would be mutual TLS via Istio or MTLS. Each GKE cluster has its own certificate authority that issues certificates valid for 5 years. It handles certificate signing requests securely. It establishes trust between the API server and kubelets, and it prevents compromise of one cluster from affecting others. Workload identity. Let's get over here. Where's the identity? All right. Workload identity enables Kubernetes applications to securely access Google Cloud services without managing service account keys. So there's a traditional approach versus a workload identity approach. Without workload identity, you'd have to generate the IAM keys manually. With it, no keys are needed. Without it, you'd have to store keys as Kubernetes secrets. With it, you'd have to use GCP managed identity tokens. Without it, you would have to mount secrets in pods. Without it, you can automatically inject tokens based on the service account mapping. Without it, you can manage key rotation. You'd have to manage key rotation. With it, you can have automatic short-lived credential managing. So how does workload identity work? Let's see. So one, you want to enable workload identity for your GKE cluster. All right. So you enable workload identity for your cluster. Then you run your workload with a dedicated Kubernetes service account. Then you create an IAM mapping between the Kubernetes service account and a G-Cloud IAM service account. You grant the IAM service account appropriate permissions. And then finally, the workload automatically receives short-lived tokens for API access. This approach dramatically improves security by eliminating the need to manage long-lived service account keys. So CIS benchmarks with GKE. The Center for Internet Security, CIS, provides security recommendations for GKE. Node security. Use container optimized operating systems. Enable shielded GKE nodes. Access control. Use RBAC. Disable legacy ABAC and implement namespaces. Logging and auditing. Enable cloud logging. Configure audit logs. Use KMS encryption and avoid storing secrets in images. Enable GKE sandbox. Restrict root access and use policies. And enable auto upgrades and patch this regularly. Additional recommendations include enable workload identity for secure service access, use network policies to restrict pod traffic, implement least privileged service accounts, disable legacy metadata APIs, encrypt secrets with cloud KMS, use binary authorization for deployment validation, monitor for security bulletin notifications, and implement pod security policies and standards. So here's a secure CI/CD workflow for containers. One, so the CI/CD work phases. There's build. This uses trusted base images, signs code, and avoids secrets in images. Scan. This implements static and dynamic analysis, checks for CVEs. Deploy. This enables binary authorization, configuring RBAC and IAM, and runtime. This monitors behavior, restricts privileges, and rotates secrets. Build phase security includes the following: using trusted resource code repos with access control, implementing strong authentication for build systems, scanning dependencies for vulnerabilities, generating and signing SBOMs, software bill of materials, using minimal base images like distroless containers, and building images with least privilege in mind. Then there's the distribution phase security. This implements proper authentication for artifact repos. It scans images before storage. It signs images with cryptographic signatures. It implements retention policies for old images and enforces access controls on registries. And then you have the runtime phase security. This deploys to hardened Kubernetes clusters. This implements pod security standards, uses network policies to restrict traffic. This enables runtime threat detection. It also monitors for anomalous behavior. It implements secure secret management, and it regularly rotates credentials. Securing containers in Google Cloud requires a comprehensive approach across the entire application lifecycle. So for the image security, this would be trusted base images, vulnerability scanning, and binary authorization. For access control, this would be IAM. This would be role-based access and workload identity. For network security, this would be networking policies, private clusters, and service mesh. For runtime securities, this would be a GKE sandbox, shielded nodes, and container threat detection. For monitoring, this would be cloud logging, cloud monitoring, and security command center. By implementing the security controls and best practices, organizations can significantly reduce this risk of container-based security incidents while taking full advantage of the agility and efficiencies that benefit containerization. So how would you do this? In the Kubernetes engine, right, you would create the cluster. So let's go to the top here. Okay. So cluster, create, name it. This is autopilot. All right. And then under advanced settings, leave advanced settings. Security, enable binary auth. All right. Secret manager, Google groups, secrets at the app layer, workload vulnerability scanning, or whatever one you needed. All right. Then you can also do service mesh, automations if needed, and click create. Okay. You can also do this in the CLI. And I'll enter that code in the correct screen. Take a look here. So you can see G-Cloud container clusters create secure cluster, zone US Central 1, enable shielded nodes, enable IP alias, enable private nodes, the master CIDR, IPv4 right here, enable network policy, and then the workload pool for the project ID, and then release channel regular, right? And you can replace project ID with your actual project ID. Also, remember to enable the binary authorization API, the following. G-Cloud services enable binary authorization.googleapis.com. And you can create an attester, right, which we talked about earlier, with the following. G-Cloud container, bin auth z, attesters, create security attester, attestation for a security note, and for the project ID. And you can create a policy that requires attestations, right? G-Cloud container, bin auth z, policy export to the policy YAML. And you can edit the policy that you just created to require the authorization. So G-Cloud container, bin auth z, policy import, policy YAML, right? And you can import that. And you could also go through the bin authorization, binary authorization, which I'll show you real quick. All right. It's under security right here. You can either create attesters or edit the policy. Let's do the edit the policy. I have to enable this API. And you can see the dollar amount here. All right. But in general, you would set the default rule to disallow all images. Then under the GKE specific rules, add a specific rule, enter the cluster's location, like US Central 1, US East 1, and then set the rule to allow certain images per your requirement. Save the policy, and you're okay. All right. You can also set up the workload identity in the CLI. We'll show you that command here. What is this? Clear? Okay. Here, G-Cloud container clusters, update, workload, project ID. Okay. And when you apply that policy from earlier, for let's say a Kubernetes service account, you can apply it the following. Okay. See that API version, service account, metadata, app SA, the namespace, you would name that as needed. Okay. You can also create IAM binding. Well, you can annotate this is a good one. You can annotate the Kubernetes service account once created with the following. kubectl, annotate service account, app SA, with the project ID and email address, and you'll be okay. Also, you can set up the workload identity. All right. This is necessary for IAM for your Kubernetes cluster. All right. For identity service here, you have to enable this identity service. This allows you to scale up with the roles for that RBAC we were talking about. All right. And I think that should do it as far as commands you can do. So here's some key takeaways. Containers provide inherent security benefits through isolation and immutability, but require proper security controls. GKE offers numerous built-in security features that should be enabled for production workloads. Container security must be addressed across the entire build lifecycle. That means build, distribution, and runtime. Authentication, authorization, and network controls are critical for secure container deployments. And finally, automation through CI/CD pipelines with security scanning is essential for maintaining secure container environments. By following all this, you can establish a secure container environment in GCP. You can leverage GKE's capabilities along with binary authorization, workload identity, and other security protocols to meet your security and compliance regulations for your industry. All right. So that concludes the main chapters of this book. What we'll do after this is go over some potential questions that you might see on a security engineer exam. Thank you for joining me and have a good day.